я думаю, что мы можем начинать вторую часть нашего семинара. Приветствуем нашего лектора.
Thank you. I'm going to give a talk that I gave at SIGIR in Beijing about a month ago. This is a paper published there called System Effectiveness, User Models and User Utility, and it presents a conceptual framework for sort of thinking about evaluation measures that are based on user models. So just to sort of set the sort of framework we're thinking about here, we're talking about effectiveness evaluation of systems. So this is system-based effectiveness evaluation using relevance judgments, queries, test collections, that kind of thing. And the purpose is just to determine how good the system is at finding and ranking relevant documents when a user submits a query. So ideally, we would like an effectiveness measure to be correlated to the user's actual experience with the engine. So when the user's experience improves with the engine, then the value of that evaluation measure should improve, and vice versa. So lately, there's been a lot of interest in effectiveness measures that are based on explicit models of user interaction with the ranked results. And so some examples of these are the rank bias precision measure of Alistair Moffat, Justin Zobel, discounted cumulative gain, which I'm sure you all know. Expected reciprocal rank of Olivier Chappelle et al. From Yahoo, expected browser utility from Emmanuel Yilmaz from Microsoft, some session measures that Evangelos is going to talk about next, and there's other work on this as well. And the purpose of this talk is to sort of classify these things and describe them in such a way that we can sort of reason about them and the properties they should have in a general sense. So this is going to be a theoretical talk for the most part, and I'll have some empirical results towards the end, but really the main focus here is on the theory. Most model-based evaluation measures are based on this basic discounted gain model of interaction. And the idea is that a user steps down a list of ranked results one by one. They gain something from the relevant documents, and they may gain something more from more relevant documents and less from less relevant documents, nothing from non-relevant documents. But the point remains they gain something from relevant documents. And then they're increasingly less likely to see documents that are lower in the ranking. And this model is usually implemented using a gain function of the relevance judgment of the document rank K, a discount function of ranks, and then the effectiveness measure is defined to be a sum over ranks of the gain divided by the discount. So that's sort of explicit in the DCG formulation, and it's also in the RBPP formulation and all these other measures as well. And it turns out that most measures can be made to fit in this basic framework, even something like precision or recall, traditional measures like average precision, R precision. You can all sort of fit them into this with just a little bit of fiddling. So I'd say that this is probably the predominant way to think about evaluation measures at this point. So I'm just going to quickly go over some of these measures, just because I'm not sure what the awareness of these is among this audience. And by the way, feel free to stop me if you have any questions. Just speak up. So this is rank bias precision. The idea here is you submit a query. Here the example query is black powder ammunition. And the engine returns a rank list of 10 results. And the user will look at the first result. They'll always see the first result. And if it's relevant, they'll derive some utility from it. If it's not relevant, they'll derive no utility from it. And then after that, the user will toss a biased coin. So this is a coin that has probability theta of coming up heads. And if it is heads, then they'll go on to the next document in that ranking. If it's tails, then they'll abandon the search and they won't look at anything else. And then the same thing happens when they get to document 2. They'll flip the coin again. If it comes up heads, they go down again. If it comes up tails, they abandon, and so on. So let's say they're looking at the first result. Let's say our biased coin has probability 0.88 of coming up heads. So they flip the coin, and essentially, you implement a coin flip as sampling from a random number generator. So let's say we sample 0.5532. That's less than theta. So we're going to say the user moves on at this point in this sort of simulation of user behavior. So then the user looks at the document rank 2. They again flip the coin. This time it comes up 0.9333, sampling from our random number generator. And that's greater than 0.8. So at this point we say they abandon the search and they gain nothing more. And we can do the same simulation over and over again. We can do it thousands of times, millions of times, billions of times. And essentially it is this sort of graphical model here, where user inputs a query. They look at the first item, and then with probability theta, they look at the next item, and theta look at the next item, 1 minus theta, they stop. And then over all of these iterations, the expected value that they get if they have a gain of 1 for a relevant document and a gain of 0 for a non-relevant document, the expected value is the sum from rank 1 to infinity of the relevance at rank k times theta to the k minus 1. So essentially, the probability of getting k minus 1 heads in a row times 1 minus theta, which is the probability of getting one tail at the end. And so this is essentially its relevance discounted by the geometric distribution function. And so we've got our gain function, we've got our discount function, and we've got the sum over ranks. So we've got our discounted gain model here. So that's RBP. The next measure. And just to sort of sum up here, these bars sort of show the relative probability of each item in this list. So there's a geometric decrease in probabilities. The next measure is discounted cumulative gain, and I think you're probably mostly aware of this. So I'll just go over briefly. In this model, we have graded judgments. So things can be highly relevant, not relevant, or perfect, excellent, good, fair, bad. We first take our ranked list, and we sort of change it to a ranked list of relevance judgments. Since here we have a relevant, not, relevant, not. These become scores, just like in RBP. So 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0. And then we discount these scores by log function of the rank in this case, and then that gives us a discounted gain. So 1 divided by log 2 of 1 plus 1 is 1. 1 divided by log 2 of 2 plus 1 is 0.63, and so on. And then finally that gives us a DCG of 2.6689 when we sum over this list. And we usually normalize DCG as well. So we normalize DCG by the best possible DCG that you could have gotten with these relevance judgments. And when we do that in this example, the NDCG, which is what it's called when normalized, is 0.91. So that's DCG, and here is again the relative. There's sort of relative discount for these ranks. And you can think of these as sort of the probability, some kind of probability that the user will see this document, and I'll sort of show how that works in a few slides here. But again, we have our gain function, we have our discount function, and then we have a sum over ranks to get the final measure. And then the last measure I'm going to talk about is this expected reciprocal rank from Yahoo, published at KCOM in 2009. And this is essentially a modification of the RBP model. So this is the graphical model that I showed for RBP. In the ERRR model, instead of a probability that you view the next item or you stop, the probability, instead of just this being sort of a flat probability, it's going to be based on the relevance of the item that you view. So you view the next item, you decide how relevant it is. If it's highly relevant, then there's some probability that you go on to the next one and some probability that you stop. If it's somewhat relevant, then there's some probability you go on to the next one and some that you stop. And if it's not relevant, there's some probability you go to the next one and some probability that you stop. And typically, this theta 1 would be the lowest probability, and theta 3 would be the highest probability. And that's to account for the fact that you're more likely to continue going on if you haven't found anything relevant, whereas you're less likely to continue going on if you found sort of the most relevant thing. So those are the those are the three measures, and then I'm also going to talk about average precision, which I hope you all know. I don't have a slide about that one, but it's sort of a traditional measure. So those three measures are they've sort of been classified into two different groups. One is the position-based models, which are the ones that are RBP and DCG. They're purely based on discounts of the rank. And then the cascade models, where the discount is based on the relevance of the documents that come up above the one that you're currently looking at, as well as the position in the ranked list. Okay. So that's sort of the introduction. So now my claim in this work is that this sort of discounted gain model is actually conflating at least four distinct models of user interaction. And if we can specify what those four different models are, then maybe we have a more formal framework in which we can think about evaluation measures and make decisions about different evaluation measures. So I'm going to formalize this a little bit. I'm going to change the rank discount function to a stopping probability distribution, which is going to be P of K. And that's going to be essentially the probability that you stop at a given rank K in the rank list. And then I'm going to change the gain function to either a utility function, so an explicit utility function based on the relevance of the documents up to some rank, or a cost function, which is a function of the number of documents you have to look at to get to some rank. And then I'm going to define effectiveness to be the expected utility or the expected cost over this distribution of stopping expectations. So this is the expected value, the expectation of variable K, expectation of the function f of K, which is either utility or cost. So we sum over ranks, the utility or cost times the probability of stopping at that K. So in this framework, yes.
So what's that?
F of K is going to be either a utility function in terms of the rank K, or a cost function in terms of rank K. And so you can plug in different functions here, and you get different measures based on what you plug in. So basically, in this framework, you have this expectation, and the components of this expectation are the stopping rank probability distribution, P of K, a document utility model, which says how much utility do you gain from a relevant document versus, maybe a graded relevance, stuff like that. And the third component is the utility accumulation model, which is the F of K, or the cost model, F of K. In this work, I'm going to stick to binary relevance, so I'm not going to talk about graded judgments. Graded judgments is kind of a future direction for this. And just to sort of put this into context of what we already saw, if you classify these measures as position-based versus cascade, we can sort of see that classification as essentially being a feature of the stopping rank probability distribution. So it's something we can use to describe a measure, and something we can use to think about measures more carefully, hopefully. And once we've defined these components, we can swap we can swap them in and out. So we can mix and match different pieces of them, and then we can test hypotheses about general properties of the components of measures. So now we can say things about general properties of stopping distributions, general properties of utility models, general properties of cost models. And then instead of trying to evaluate each possible measure as its own individual entity, we can evaluate measures, or we can evaluate measures in terms of the properties they have in these three dimensions. Okay, so my argument is that depending on the choices we make in the P of k, the F of k, and essentially P of k and F of k, we have four distinct models of user interaction. The first model is going to be expected utility at some stopping point, and I'll talk more about what all these mean, of course. The second model is expected total utility at a stopping point. The third model is expected cost to get to some stopping point, or expected cost to achieve some level of utility. And the fourth model is expected total utility per unit cost expended by the user in browsing the ranked results. For each one of these models, I'm going to have an exemplar measure, which is going to be among the measures that I talked about already. And so hopefully that will sort of illustrate how these things are characterized and how you can think about them. Okay, so the first model is the expected utility at stopping rank. And the exemplar here is rank biased precision. So rank biased precision, if you look at it as an expectation, you have a probability distribution here, theta to the k minus 1 times 1 minus theta. This is the geometric probability density function. And you have your F of k, your utility, rel sub k, and you have your sum. And so essentially what this measures is effectiveness as the expected relevance of the document at the rank the user is stopping at. And that means essentially intuitively what this means is that there's only one document that matters to the user, and that's the one that they stopped at, or the one they looked at last. And so that's why I call this expected utility at the stopping point. The second model is called expected total utility, and the idea here is that we sort of convert our thinking from we convert our thinking about stopping probabilities to thinking about viewing probabilities. And so we say, what is the probability that the user would see the document at rank k rather than the probability the user would stop at the document at rank k. So if a user is going to stop at rank 1, that means they saw rank 1. They saw the document at rank 1, and that's all they saw. They didn't see any of the other documents. If the user stops at rank 2, then they saw the document at rank 1. They saw the document at rank 2, and they didn't see any other documents. If they stop at rank 10, they saw all the documents from ranks 1 to 10, but then they didn't see anything after those. So essentially the probability of viewing the document at rank k is the sum of the probabilities of viewing all documents from k onward. So the probability that you see the document at rank 2, for instance, is the probability of stopping at rank 2 plus the probability of stopping at rank 3, because if you stop at rank 3, you see rank 2. Stopping at rank 4, because if you see rank 4, you see rank 2, and so on. So we'll call that F of k, and F of k is essentially a cumulative probability density function. And so in the discounted gain model, we can think of the relevance judgment as being the gain, and now we can think of the cumulative density as being the discount. And then I would argue that DCCG is the exemplar measure for this class, where F of k is the cumulative function. F of k is the DCG discount based on logs. and summing over this gives DCECG. So I'll show how that works here. So sorry, this is a lot of math. As I said, this is the theoretical kind of work. So if we take this as our measure formulation, so we have a relevance, a gain times a discount, or relevance times a cumulative density function. What we want to do is turn this into something that looks more like a utility function times a probability distribution, or probability. So it's an expectation, and this is not expectation. So we first plug in our formula for f of k, which is the sum from k to infinity of the stopping probability. And then once we have this, we can re-index this. We can flip these things around a bit, and we get this instead. So now we're summing from k equals 1 to infinity times the stopping probability times the sum of I equals 1 to k of the relevance stretchment at rank I. And this quantity here is just the number of relevant documents that you see by rank k. So then we have r sub k here is equal to this, and r sub k times p sub k is an expectation. This is the expected total number of relevant documents you see if you stop at rank k, and then we have our expected utility formulation. So this is the general way to do this, the general conversion from the discounted gain formulation to the expected utility formulation. To get DCG out of this, we define our cumulative density function as 1 over the log of k plus 1, which is the DCG discount. And then once we have that, then we can define p of the DCG stopping probability as the cumulative density of stopping, or of viewing k minus the cumulative density of seeing k plus 1. And you can sort of see, you can work out how that works if you want. And then we have a stopping probability for DCG, which is 1 over the log of the rank minus 1 over the log of the rank plus 1, essentially. And so then you can plug this probability into this formulation, and then you can work the algebra backwards, and then you show that you get binary relevance DCGG, except that you're summing to infinity instead of some fixed rank. All right, so is that clear? I hope. Okay. Our third model is the expected cost model. And the idea here is that a user stops with some probability that's based on the total accumulated utility rather than based on the rank alone. So this is the distinction between the position-based and cascade-based models that I talked about in the introduction. So now P of k is actually going to be equal to P of R sub k. So now the stopping is based on the total amount of relevance you've accumulated rather than on the rank that you're looking at. And if the document rank k is not relevant, then we assume that you're not going to stop at that rank. So the stopping probability there is 0. And now f of k is going to be the cost of going to rank k rather than the utility that you achieve at rank k. And so the exemplar measure for this class of models, or this class of user behaviors, is the expected reciprocal rank, or ERR, except with binary relevance rather than graded relevance as they originally discussed in their paper. So the P of k is going to be rel sub k times this probability theta, which is the same probability as in RBPP, except now it's to the power of r sub k minus 1 rather than k minus 1, and then times 1 minus theta for the stopping point. So the rel sub k here is just basically, it's just capturing this if and otherwise statement. So if it's not relevant, then the probability will be 0. If it is relevant, then the probability will be this geometric distribution. And then our cost function is going to be 1 over k. So essentially this is going to be it's actually a 1 over cost function or inverse cost function or reciprocal cost function. So it's 1 over the number of documents you have to look at to achieve this r sub k level of utility. And let me see here. So this is if you look at the formula for ERR, it's 1 over k times rel sub k times theta to the r sub k minus 1 times 1 minus theta. In the discounted gain framework, the rel sub k is the gain, and 1 over k times this is the discount. In the utility or expected utility framework, the expected cost framework, 1 over k is the cost, and this is the probability of stopping. So what this shows is that sort of by changing where you put the parentheses in this expression, you can change it from a discounted gain-based measure to an expected utility measure. And then finally, the last model is expected utility per unit cost. And what I mean by this is that every time the user gets to some rank k, they basically consider the effort or the expected effort of further browsing down that ranked list. So if they get to rank 2, they think about how much effort they're going to expend going down further ranks, how much utility they expect to gain from that, and then they decide whether or not to do that based on that trade-off or based on that thinking. So the model is at a rank k, they gain the relevance of the document at rank k, and then they look ahead and they say what is the expected cost or expected utility of going further from that rank. So this is our discounted gain formulation. This is the gain. This is the discount, and then we have our sum over gains times discounts. We can do the same thing we did with DCG and the M2 family. We can manipulate this algebraically, change the indexes around, and then instead of this, we get this. And now we have a cost, basically a cost and a utility combined in here. So R sub k is utility, total number of relevant documents seen. F of k is cost, total cost of going to rank k, and P of k is the probability, and then we have a sum which makes it an expectation. So if we set f of k to 1 over k, so 1 over k is the same thing we use with ERR. In this case, if we set it to 1 over k, what we get is 1 over k times r sub k. This should be, this should be familiar as being equal to precision at k. So we get precision at k times P of k. And so essentially precision at k is basically utility per cost, and then P of k is the probability of stopping. And then the average precision measure is our exemplar for this. If we set P of k equal to the relevance of the document at rank k divided by the total number of relevant documents, then we get then this is equal to average precision. So I hope this is all clear so far. I will summarize this. Basically, I've introduced four ways to turn a sum over gains times discounts into an expectation over stopping ranks. And these four ways have four distinct sort of models of user behavior attached to them. Each one of these models has a measure or an exemplar measure from the IR literature. So M1 has an exemplar of RBP, M2's exemplar is DCG, M3's is ERR, M4's is average precision. We have four different stopping probability distributions. So we have the RBP distribution, which is geometric, the DCG distribution, which is this odd difference between reciprocal log ranks. We have the ERR distribution, which is this geometric distribution times a relevance judgment to make it an if or else kind of distribution. And then we have our AP distribution, which is based on the total number of relevant documents. And to these four, I'm going to add two more, which are interesting. One of them is what I'm going to call the reciprocal rank distribution, although it's actually a reciprocal quadratic rank. And this is 1 over k squared plus k. And then the other one is this reciprocal relevant rank distribution, which is going to be 1 over r sub k. Excuse me. 1 over r sub k squared plus r sub k. And I'm not going to talk too much about why these are interesting, but I'll discuss it briefly. Okay, so we have, as I said, now we have six stopping probability distributions. This plot sort of compares their respective probabilities of stopping at each given rank. So on the x-axis here we have ranks from 1 to 25. The y-axis we have our stopping probability. The dark blue line or the purple line here is RBP's stopping probability function. This orange dashed line is DCG's stopping probability function. When we characterize DCG as our M2 family. And the dotted orange line, which is hard to see here, but it's in between the two for the most part, is our reciprocal rank stopping distribution. And what you can see from this is that the RBPP model and the DCG model are actually quite similar in their stopping probabilities. And so essentially by doing this algebraic manipulation to DCG, it actually turns out that DCG is modeling a stopping distribution that's very similar to RBP's stopping distribution. And this is something that you wouldn't think of just by looking at these two measures, and certainly something that people have not thought of in the past, looking at these two measures. So what I mean by this is that we can say the difference in RBP and DCG does not come down to their discounts in the stopping distributions, because they're fairly similar in that respect. It comes down to how they model the utility accumulated by the user as they step down the ranked results. I will mention one other thing here, which is the fatness of the tails. So as we can take these distributions out to infinity, and as we take it out to infinity, RBP goes to zero very fast. DCG goes to zero much slower, and RR, the reciprocal rank distribution, goes to zero in between those two. And so I'm going to characterize DCG as having a fat tail, RBP as having a thin tail, and reciprocal rank is having a sort of medium weight tail. And that's going to be somehow a way to characterize differences between measures in terms of their stopping probability distribution. And so here this shows the cumulative density functions for these three measures. And here it's much more obvious. The differences between these measures is much more obvious, and you can see the fat tailness of RBP, fat tail of DCG here as compared to the thin tail of RBP when you look at the cumulative densities. We can also look at the dynamic distributions. So these three are static. They're static in the sense that they only depend on the rank. They don't depend on the relevance of the documents up to that rank. The other three distributions are dynamic in that they do depend on the relevance of the documents at the rank you're looking at. So the ERR distribution is just geometric, but it only has density at the points at which relevant documents appear. So here we have relevant documents at ranks 1, 2, 3, and then 5, 8, 11, and so on. And so those are the only points that have density. The AP distribution is similar, except it's uniform over points where relevant documents appear. And the reciprocal rank distribution again is in between the two, essentially. And we can also look at the cumulative densities of these three. And again, we see that here we see that AP has a very fat tail in the cumulative density. ERR has a much thinner tail in the cumulative density, or it sort of shows up in the cumulative density graph. And the reciprocal rank distribution has something in between. Yeah. Yeah, the spikes are the places at which relevant documents appear. So this is an artificial ranking.
Okay.
And it's just an example, but if you had a different example, you would see spikes in other places. Okay, so now essentially we can go now to go from the models to the actual measures. Basically, what you do is you just mix and match. You can take one of these probability distributions. You can take one of these utility accumulation model families, and you put them together, and you get a measure out of it. So we have 6 probability distribution functions, and we have four model families. So in principle, we could have up to 24 different measures in this framework. Now it turns out that a lot of these are not interesting measures. They basically some of these turn out to be constant valued, so they're not based on the relevance or the ranking at all, and those are not interesting. So some of them are just isomorphic to precision or isomorphic to recall. So those are not interesting because we already have precision and recall. And so it turns out that 9 of them are not interesting, and 15 of them are interesting. So these 15 that are interesting are the ones that we're going to study. And here they are. So here in this column we have a probability distribution along the along the rows we have probability distributions. Along the columns we have model families. And if you take a model family and a probability distribution, you get a measure. So we have RBP as one of our exemplars. That's where we take M1 and RBP probability. DCG comes when we take M2 and the DCG probability. ERR when we take M3 and the ERR density function. And AP comes when we take model 4 and the APP distribution function. But then we can also take M1 with PDCG, and then we get a measure that I call cumulative discounted gain. So I have little names for these that hopefully make it sort of clear what they're supposed to be. We can take model 2 with the RBPP function, and then we get rank biased total relevance instead of rank biased precision. We can take M4 with PRBP, and we get what I call rank biased average precision, because now it's a expected value of precision rather than expected value of the relevance of the last document. And so all these things are sort of this way. So we have 11 new measures here, along with our four measures from the IR literature. Okay, I'm going to just quickly cover a few other things which are covered in more detail in the paper. Again, our 2011 paper. The reciprocal rank distributions come up when you integrate this geometric density function from theta over theta. So you integrate from theta equals 0 to theta equals 1. It turns out that when you integrate it that way, you get this 1 over k times k plus 1 discount. And the intuitive idea there is that if you don't know what the user's sort of probability of going down the ranked list is, then you might try every possible value of that, and trying every possible value of that is exactly equivalent to integrating over that variable theta. And so that's where this comes from. And then when we take the cumulative form of this distribution, it's approximately equal to 1 over k. And 1 over k is often used in DCG, so sometimes people use DCG with a reciprocal rank discount, and they'll call that reciprocal rank DCG or something like that. And so that's why this is interesting. The second point is this normalization. So we talked about normalizing DCG to get NDCG. It turns out that every measure in the M2 family, or every measure in the family that DCG is representative of, has to be normalized in a similar way. And so we will do that in our sort of analysis. There are some of these other measures, like ARRR here does not naturally fall between 0 and 1. So for those measures that don't fall between 0 and 1, we normalize them so that they do fall between 0 and 1. And then finally rank cutoffs. So as I mentioned, as I presented this DCG formulation, it only works if you're summing from ranks up to infinity. Now in reality, of course, you never sum to infinity. You usually sum to 10 or 5 or 3 or something like that. And that's much less than infinity, and the math doesn't work out in that case. But it can actually still fit the user model. And I have some math that's worked out in the paper. I actually think there's a better way to do it now, thanks to some discussion at SIG-IR. But essentially, it essentially doesn't matter if you're summing to infinity or summing to some small k. The math works out either way. Okay. So the purpose of this, basically, I've put together a framework, and I've showed you how you can get new measures out of this framework. The purpose of this is to sort of make hypotheses about properties of measures, and then test those hypotheses using actual measures or something like that. So some of the questions we can sort of ask, or some of the hypotheses we can raise are the models that are based on utility better than the models that are based on cost or effort? So in other words, are M1 and M2 families better than our M3 or M4 families? And our hypothesis is that there's no real difference between those two. This is just a sort of intuitive hypothesis. It's not based on data at this point. We can ask whether measures that are based on stopping probabilities are better than measures that are based on viewing probabilities. So is RBP better than DCG, for instance? Our hypothesis here is that the ones that are based on viewing probabilities are more robust than the ones that are based on stopping probabilities. We can ask what properties the stopping distribution should have. So should it have a fat tail? Should it have a thin tail? Should it have a medium tail? Should it be static? Should it be dynamic? We can come up with a lot of properties of probability density functions, and then we can test whether those are good properties or not good properties. So these are the kinds of questions we're going to ask, and there's a lot of other questions we could ask. Essentially, there's sort of entire suites of questions we could ask. And so we could ask how well measures correlate to user satisfaction, or how well do our stopping probability distributions actually model users. How robust are these measures to changes in the underlying data, such as changes in relevance judgments, changes in the topics, changes in test collections. How good are these measures for optimizing systems? Sort of how discriminative are they for identifying differences between systems? We can ask how informative they are. So how much do they tell us about the relevance of individual documents when we look at them in aggregate? And I'm really in this work I'm mainly going to focus on how robust these measures are. But this question of how well they correlate to user satisfaction is probably the most important question in the end. And so I'll talk briefly about it here. And the question here, I guess, we can ask is how well does a stopping distribution fit to empirical click probabilities? Now, of course, we can look at click distributions. It's obviously not the case that if somebody clicks on something, that means that they stop their search at that point. But we do need, we have the click log. We can't ask the users why they stopped or where they stopped. So we have to make some assumption about what they're doing there. So we need some model at the stopping point. if we're going to correlate this to user behavior. And a click is sort of a decent proxy for that. And the idea here is that if we have a good fit between the click distribution or empirical click distribution and the model density function, then that probably indicates that we have a good model of the stopping point. And so here is some results. Yeah.
Would it make more sense to compare viewing probability to clicks?
So you mean in the sense that if somebody clicks at rank 10, he has viewed all those documents up to that point? It's a good question. It might be. I think it's worth thinking about. I don't have those results here though. So what I've done here is I've taken the AOL log, which you saw presented in the last session, and I just counted the number of clicks that occurred at rank 1, counted the number at rank 2, counted the number at rank 5, and so on, and then divided by the total number of clicks, and that gives an empirical stopping distribution. So that's the black line here, and you can see it sort of makes sense. Users they get less likely to click because they go to rank 10, and then there's a big drop off because they have to go to the next page to see the next 10 results, and then there's a decrease, and then a big drop off, and so on. So this is on a log scale, both the x and y axis. And the AOL data goes all the way down to rank 500. So there are recorded clicks at rank 500, and even recorded clicks past rank 500. But those are all aggregated at rank 500 for this data. And so we'll compare this to our three stopping distribution functions. So the blue line here is RBP. And basically, you can see that RBP models this fairly well up to rank maybe 4 or so, but then it has a huge drop off, and so the geometric stopping probability can't really model this long tail of clicks. The DCG distribution tracks this pretty well up to maybe rank 30 or so. And then they start to diverge with DCG predicting more clicks, or maybe some higher probability of stopping at ranks after that. It turns out that the best predictor here is actually the reciprocal rank distribution, which tracks pretty closely all the way down, maybe to rank 300 or 400 or so, before it starts to diverge. So there's some sense in which, if you believe this model, if you believe both models here, then there's some sense in which maybe this reciprocal rank sort of tracks user clicks better than either of these other two models. Now, of course, this is all contingent on this particular data set. It's possible that if you looked at, this is from 2006 AOL search engine. It's possible that if you looked at modern data from Microsoft or Yahoo, you would see a steeper decline in clicks. It's also possible, maybe we should also look at the cumulative distributions instead of probability distributions, and then we would see something else. But this at least shows there's some suggestion here that maybe this reciprocal rank distribution fits the click data the best of any of these. But it's by no means the final word on this. Okay, so now I'm going to move into robustness, and I'm going to cover this fairly quickly because it's it's kind of technical. So the question here is, how robust is the measure to changes in the underlying test collection data? So test collection consists of a topic sample, relevance judgments, and maybe some pool depth of the judgments, or some process for acquiring the relevance judgments. If we change the question is if we change the topic sample, do the measure values change substantially, or do we make different decisions about relative effectiveness of systems. If we change the relevance judgments, do we make different decisions about relative effectiveness of systems? If we have more judgments or fewer judgments, do we make different decisions, and so on? And we would like the decisions we make to be as consistent as possible, as much as these things change. So in the paper, I look at 3 different test collections. In this presentation, I'm just going to look at one of these. So first, we have data from the TREC-6 ad hoc track. I don't know if you guys all know how TREC works, but basically at TREC, the organizers put together a set of topics. In this case, 50 topics. They distribute them to sites that are going to participate in TREC. So those are universities, companies, individuals maybe, and those participating groups run that set of topics on their retrieval systems, and they produce runs. And those runs are submitted to TREC. Then TREC takes those runs. They do a union of maybe the top 100 results or something like that, and they have those top 100 results judged for relevance. So in this case, it produces 72,270 unique relevance judgments, and this was on a document on a corpus consisting of 550,000 documents, which were mostly news articles at that time. I think this was in 1996 or 1997, I think. And this TREC-6 ad hoc is interesting because, first of all, it has a very large number of judgments. It has a very large number of submitted runs, so we can compare differences between measures when we change underlying data. And it also has a second set of relevance judgments that came from the University of Waterloo, and that disagree with the original judgments in some significant ways. I won't talk about the other two, but you can see them there. So our experimental methodology here is that we're going to pick some part of this test collection to change in some way. So we might change the judgments, we might change the topic sample size, we might change the pool depth, and then we're going to evaluate all 74 of the submitted runs with TREC's gold standard data. We're going to evaluate all 74 of the submitted runs with the data that we changed in some way. And then we're going to compare the first evaluation to the second evaluation using some kind of rank correlation. So basically what that means is that we're going to say, if we're looking at RBP, for instance, we're going to evaluate all 74 systems with RBP with the gold standard data, evaluate all 74 systems with RBP with some subset of the gold standard data. And then we're going to look at the ranking of systems by RBP in both of these experiments and see how closely they're correlated to each other. And the purpose of this is to determine which properties of measures, or which properties of these families are most robust. So the specific things we'll be looking at are the model family, the tail fatness, and whether the distribution is static or dynamic. Okay, so the first experiment is varying the relevance assessments. So we did our whole experimental setup. We evaluated with TREC's relevance judgments. We evaluated with Waterloo's relevance judgments, and then we calculated Kendall's tau correlation between the two rank lists, or some measure of association between the two. And what to look at here is basically. So each one of these cells is a Kendall's tau correlation. Generally, 0.9 is sort of the standard. 0.9 is what you're trying to achieve. So if it's less than 0.9, that's considered to be not it's considered to have some significant differences between the two rankings. So we see that our RBP, among our 4 measures, our RBP has the worst tau correlation. DCG has the best. And AP is pretty much right at 0.9. But what we're really interested in here is the general properties, so the average tau correlations over the columns and across the rows. And so the average correlation of the first model is 0.821, whereas for the second model it's 0.8865, which means that the second model is much more robust to changes in the relevance assessments than the first model is. And it's also much more robust than the third and fourth models are. Now, one hypothesis we had here was that M2 and M4 would be better than M3 and M1, and it turns out to be not the case here. So it looks like M3 and M4 are roughly equal to each other, but if you remove AP here, AP is essentially an outlier in this data. It's much higher than anything else in this column. This goes down a lot, and it turns out that this ERR model is much more robust. If we look across the rows, we see that the fatter tail distributions are more robust than the thinner tail distributions. So DCG has the highest tau correlation across rows. AP has highest across rows. And then if we look at the average for static distributions and the average for dynamic distributions, it turns out that they're pretty much the same as each other. So the takeaways here are that the M2 family seems to be most robust to changes in relevance assessments, followed by M3 after we remove this outlier. The fatter tail distributions appear to be more robust.